Welcome back to the deep dive. Today we are going to perform a bit of an exorcism, or maybe more accurately, a corporate restructuring of the mind.
An exorcism. That's a pretty dramatic way to start a Monday.
Well, just stick with me here. I want you to picture the brain,
Hmm.
and specifically, I want you to picture where you live inside your brain.
Okay.
When you think about focus or planning or willpower, I mean, basically the act of being a functioning adult, what's the image that pops into your head?
For most people, they point right to their forehead. The prefrontal cortex.
Exactly. We have this very persistent, very seductive myth of the executive brain. The CEO,
The homunculus, yeah.
the little guy in the chair,
Mm.
the big boss sitting in the corner office right behind your eyes, just barking orders, making all the decisions, steering the ship. It's a very unitary idea. One boss, one controller.
It is a very common metaphor. And it makes sense, intuitively because our conscious experience feels singular. But, and this is the key thing we're getting into today, it's almost entirely wrong.
Right. Because today we're looking at a stack of research that suggests your brain isn't run by a CEO, it's run by a committee,
A very busy committee.
or rather a very complex, high-stakes boardroom with really specialized departments that, don't always get along.
That is a much more accurate, if maybe slightly more chaotic, analogy. We're going to be debunking this whole unitary model of control.
So we're moving past the idea that cognitive control is just one thing happening in one place.
We're looking at distinct, separate networks.
Specifically, we're going to meet two major players that control your life, yet most people have never even heard of them, the FPN and the CON.
The frontoparietal network and the cingulo-opercular network.
They sound like rival political parties.
In a way, they are governing bodies. I mean, these are the systems that let you switch tasks or stay focused during a really boring meeting or learn new rules. And we have a really comprehensive stack of papers to get through today to understand them.
We do, so lay it on us. What are we working with?
Okay, so we're anchoring this whole deep dive on some really foundational work by Nico Dosenbach and his colleagues. We've got distinct brain networks for adaptive and stable task control in humans from 2007,
Okay.
and their critical follow-up, a dual networks architecture of top-down control from 2008. These are the papers that really cracked the code on this two-network system.
But we're not just stopping at 2008. We're tracking how this idea has evolved.
No, absolutely not. We're also pulling in a crucial 2014 paper by Settagiani and Desposito about something called tonic alertness, which completely changes how we view that second network, the CON.
Okay, so a big update to the model.
A huge one. And then to bring us right into the modern era, we've got three massive reviews. There's Menon and Desposito's 2022 paper on PFC networks, another great one from Friedman and Robbins in 2022 on executive function, and finally, we're looking at a 2025 review on cognitive control by David Badre.
So we're covering, almost 20 years of neuroscience evolution here?
We are, and the mission really is to dissect exactly how you, the listener, manage to stay focused in a world that is pretty much designed to distract you.
All right, let's jump in. Section 1, the paradigm shift.
Let's do it.
So take me back. Before 2007, what was the prevailing wisdom? If I'm a neuroscientist in, say, 2005, and I put someone in an MRI scanner and I give them a hard task like complex division or something, what am I looking for?
You're largely looking for the executive. I mean, most researchers were focused so heavily on one particular spot, the dorsolateral prefrontal cortex, the DLPFC.
Right, the front and center part.
Exactly. They saw it lighting up whenever things got hard, and the assumption was that it was the Lone Ranger. The general idea was that as tasks got more complex, this one region just worked harder. It was a very unitary model, one system for all of control.
Okay, so how did Dosenbach and his team figure out that this wasn't the whole story? I mean, how do you even go from it's one boss to it's two distinct networks?
Well, it really comes down to the methodology, and this is actually really cool. Back in 2007, Dosenbach used a specific fMRI technique called mixed blocked event-related fMRI.
Okay, let's unpack that, because usually fMRI studies are one or the other, aren't they?
They are, correct. Traditionally, you either look at the brain in blocks, so something like do this math task for 30 seconds, then rest for 30 seconds, on and off.
Right.
Or you look at events like, here's a picture, boom, what happened in the brain right at that exact moment.
And I guess the problem with the blocks is that it just blurs everything together. It's like taking a long exposure photograph of a highway. You just see these streaks of light. but you can't tell if it's one car moving really fast or 100 cars moving slowly.
That is a perfect analogy. It's a
Yeah.
perfect analogy. And the other way, the event-related design, it kind of misses the forest for the trees. It's all about those individual
So
moments.
Dosenbach combined them.
He combined them. And this allowed his team to mathematically separate brain activity that happens moment to moment, like when you see a start cue or you realize you've made a mistake, from the activity that turns on and just stays on for the entire duration of the task.
Ah, I see. So they could separate the engine turning over from the engine just humming while you drive down the road.
Precisely. And when they did this, when they separated those two types of signals, they found that the brain activity didn't just overlap into one big blob. When they analyzed the data using graph theory, which looks at how different regions connect and talk to each other,
Yeah.
the regions separated into two completely distinct networks. They weren't just one thing working harder, they were two different teams doing two different jobs.
Okay, let's meet the players then. Network number one, the engine turning over.
This is the frontoparietal network, or FPN. Anatomically, this includes that famous dorsolateral prefrontal cortex, the DLPFC we mentioned.
The old CEO.
The old CEO, exactly. But it also includes the intraparietal sulcus, or IPS, the inferior parietal lobule, the precuneus, and the mid-cingulate cortex. So it's a whole constellation of regions.
And what's his job? Dosenbach gives it a very specific label.
He does. Rapid adaptive control.
Rapid adaptive control. Okay, I want to dig into the vibe of this network. Based on that data, how does it actually behave?
The vibe is jumpy, it's reactive, it's a bit frantic, actually. This network lights up huge right at the start of a task.
Okay.
Then it lights up again if you make an error. It's operating on a trial-by-trial basis. It's constantly checking in. What's the rule right now? Did we just mess up? Okay, fix it next trial. It's very in the moment.
So, to use a sports analogy, this is the quarterback.
Yes, that's a great one.
Or maybe a crisis manager. It's the one calling the play at the line of scrimmage. It sees the defense shift, it screams Omaha, and changes the play right at the last second. It snaps the ball. Then, 3 seconds later, it's doing it all over again. It lives in the immediate future.
That is exactly it. It's all about flexibility. And in fact, Dosenbach's paper notes that the FPN connects really strongly to the cerebellum.
Which is usually for motor control, right?
We used to think so, but we now know it's heavily involved in error processing, cognitive error processing. So the FPN gets that oops signal from the cerebellum and adjusts the control settings almost instantly. We're talking within seconds. If the rules of the game change, the FPN is the one that notices and pivots.
Okay, so that's the quarterback. Essential. But a quarterback can't play the game if the stadium lights aren't on and the field isn't maintained. So
Yeah.
enter network number 2.
The cingulo-opercular network, or KEEP-MN.
This sounds a bit more obscure. Where is it in the brain?
It's anchored much deeper in the brain. It includes regions like the dorsal anterior cingulate cortex, or DACC, the medial superior frontal cortex, the anterior insula, the frontal operculum, and the anterior prefrontal cortex. And it also has strong connections to the thalamus, which is like a central relay station.
And its function?
Stable set maintenance.
Stable set maintenance. So contrast the vibe here. How is this different from the FPN?
The CON is the complete opposite of jumpy. When a task block starts, the CON end turns on, and it just stays on. It's like flipping a switch. It creates the stable background mode.
So it's holding the state.
It's holding the state required to perform the task. It doesn't spike with every individual trial. It actually seems to ignore the little bumps in the road, the little errors, in order to maintain the overall destination.
So if the FPN is the quarterback calling the plays,
Yeah.
the CON is, what? The coach on the sideline. The stadium manager.
I really like the idea of a stage manager in a theater.
Ooh, I like that.
The stage manager makes sure the lights are focused, the props are in the right place, the noise is kept down backstage. They create the entire environment for the actors, the FPN, to do their job. If the stage manager walks away, the whole play falls apart, even if the actors know their lines perfectly.
That makes so much sense. It's the platform, it's the context. Now here is where it gets really, really interesting for me. In the 2008 paper, Dosenbach and his team dropped this fascinating biological detail about the CON, von Economoneurons.
Yes, this is one of my absolute favorite details in all of neuroscience. Von Economoneurons, or VNs, are these very large, spindle-shaped projection neurons. And here's the kicker. They are not found in all mammals. You don't find them in mice. You don't find them in cats. They're quite rare.
So where do you find them?
They are abundant in humans. You find them in great apes, in whales, in elephants.
Huh. Highly social, intelligent animals.
Exactly. And where in the human brain are they most concentrated?
Let me guess. The CON.
They are specifically concentrated in the anterior cingulate and the anterior insula, the exact hubs of the cingulo-opercular network.
That feels profoundly significant.
It is. It really is. It suggests that the CON is a phylogenetically newer system, evolutionarily speaking. This ability that we have to maintain a stable task set over a very long period, to hunt for hours, to write a thesis over months, to record this deep dive right now, that might be what makes us uniquely human.
Wow. So other animals are living very much in the now, reacting to stimuli with their FPN.
Right. They're very reactive.
But humans can hold a mode for days or even years, and that's the CON.
That's the CON, and that connects to the broader dual network architecture concept they proposed. These aren't just two blobs working together. They have a very specific relationship.
Right. It's not hierarchical. It's not the prefrontal cortex bossing everyone else around, which was the old model.
Exactly. Dosenbach proposes a parallel processing model. The FPN and the CON work side by side in parallel.
And they use a small world architecture. What does that mean?
That's a term from network theory. It basically means you have dense local clustering. So everyone within the CON department talks to everyone else in the CON department a lot.
Okay, they're gossiping.
Right. But you also have these efficient long-range shortcuts to other departments. So the CON has a direct line to the FPN and to motor systems and so on. It balances efficiency with resilience.
How does it help resilience?
Well, if your quarterback, the FPN, gets confused for a second, the stage manager, the CON, is still holding the set. The lights are still on, so you don't completely lose the plot. The whole system doesn't collapse because of one little error.
Okay, so synthesis time for section 1. The executive is actually a duo. You've got the FPN, which is the adjuster rapid phasic reactive.
And the CON, which is the maintainer stable, tonic, enduring.
Precisely. It was a beautiful, elegant model.
There's always a but.
Of course. Science moves on.
And there was a mystery brewing about the CON. Dosenbach called it task set maintenance, basically remembering the rules of the game.
Right.
But other researchers were looking at those same brain areas, the insula, the cingulate, and they were calling it the salience network, which is about detecting what's important. And then in 2014, Satagiani and Desposito threw a huge wrench in the gears.
I love a good wrench. Let's get into section 2. The deep dive into the CON.
All right, so here's the conflict. Dosenbach says the CON is holding the rules of the task, like press left for red, right for blue.
Okay.
But Satagiani looked at all the data and said, I don't think it's about the rules at all. I think it's about alertness.
Tonic alertness. That sounds like something you'd buy in a bottle at a gas station. Define that for us in a neuroscience context.
Tonic alertness is the intrinsic capability to keep your cognitive faculties online and available for processing, regardless of the specific content of the task. It's not about what you are doing, it's about the fact that you are ready to do it.
So it's not the knowledge, it's the readiness.
It's the readiness, it's the state of being prepared.
Okay. So how on earth do you test the difference? How do you separate knowing the rules from being alert?
You design a really, really clever experiment, and that's what Satagiani did. They used a continuous pitch discrimination task. So you're just sitting there listening to beeps, and you have to tell if the pitch is high or low.
Sounds thrilling.
It's psychophysics. It's not meant to be fun. But here's the genius part. They manipulated two different things completely independently. First, they manipulated selective attention. They made the difference between the high and low pitch tiny. Really, really hard to hear the difference.
Okay, so that's hard work. You have to really, squint with your ears to do that.
It is. It takes a lot of effort. And when they did that, it recruited the dorsal attention network, or DAN, which we'll get to in a bit, but it did not recruit the CON.
Wait, really?
Really? Just making the task harder didn't wake up the stage manager.
That's so interesting. So simple difficulty isn't the trigger. What was?
Factor 2, jitter.
Jitter? What do you mean?
Yes. So instead of a nice rhythmic beep, beep, they messed with the timing. It became beep, 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 beep. Completely unpredictable.
Oh, I can feel my blood pressure rising just thinking about that. It forces you to be constantly on edge. You can't relax.
Exactly. It forces you to stay on guard continuously because you have no idea when the next stimulus is coming. And this specific manipulation, the temporal uncertainty, drove the CON wild.
So the CON doesn't care if the math problem is hard. It cares if you don't know when the math problem is going to show up.
In a way, yes. The conclusion from this paper was that the CON isn't just holding rules. It's maintaining an effortful state of readiness. It's suppressing the internal and external noise so that you are prepared for whatever comes next, whenever it comes.
And they actually proposed a physiological mechanism for how it does this, right? The windshield wiper.
Yes, this is where it gets really fascinating. They found that activity in the con correlates with global power in the upper alpha band. That's about 10 to 12 hertz. Now, for a long time, we've known that alpha waves in the brain are usually inhibitory. They quiet things down.
Which seems totally counterintuitive. If I'm super alert, shouldn't my brain be turned up? Shouldn't it be buzzing with high-frequency gamma waves or something?
You would think so, but think about it this way. If you're in a noisy room and you're trying to hear a whisper, do you start screaming louder yourself?
No, you. You tell everyone to be quiet.
You hush the room. Satagiani proposes that the con uses these alpha waves like a rhythmic windshield wiper to clear out neural noise and distraction across the entire cortex.
I love that analogy. So it's active noise-canceling headphones for your brain.
Yes, that's it exactly. The con doesn't play the music, that's the job of the FPN or the sensory cortices. The con just creates the quiet room so you can actually hear the music clearly.
That radically changes how I think about focus. Focus isn't just trying really hard to look at something, it's actively suppressing everything else. And that's the con's job.
Correct. And this brings us really nicely to the broader cast of characters, because the FPN and the con, as important as they are, aren't the only networks in this boardroom.
Okay, section 3, the broader cast.
Yeah.
Who else is at the table?
So for this, we really need to bring in Menon Desposito's 2022 review. We have the adjuster, the FPN, and we have the maintainer or the noise canceller, the key on. Now we get to meet the spotters.
Thanks, spotters.
The dorsal attention network, or DAN. This network involves the frontal eye fields and the intraparietal sulcus. This is your top-down voluntary spatial attention. This is the network you use when you say, I'm looking for my keys on this messy desk. It's very directed and intentional.
Yeah, and there's another attention network.
There is the ventral attention network, or VAN. This is the circuit breaker. It involves the inferior frontal gyrus and the temporoparietal junction. This network is a bottom-up system that reacts to unexpected salient stimuli.
Like a loud bang.
A loud bang, a flash of light. It's the network that breaks your focus on the keys to tell you, hey, there might be a tiger in the room.
So the DAN is, look at this, and the VAN is, hey, look at that.
Exactly. And then, sort of lurking in the background of all of this is the default mode network, or DMN.
The daydreaming network.
The daydreaming network, yeah. It's active when you are resting or mind-wandering or thinking about yourself or others, and it's usually anti-correlated with these control networks. When the CON and FPN go up, the DMN usually goes down.
Right, you can't really perform surgery while you're thinking about what you're going to have for dinner.
Ideally not, no. But here's where we get into a bit of a turf war in the literature.
Ooh, academic drama.
A little bit. We mentioned earlier that some people call the HAN the salience network. Vinod Menon, in his 2022 review, argues very strongly for a distinct salience network, or SN, that is anchored specifically in the anterior insula.
So how is that different from the CON? Isn't the anterior insula a core part of the CON?
It is. It's a nuance of anatomy and timing. Menon sees the salience network's primary job as being the switch. He proposes this triple network model. You have the DMN for internal thought and the FPN for engaging with an external task. The salience network sits right in the middle.
Right, it is what?
It detects a biologically relevant event that could be pain, a potential reward, seeing an error you made, and it toggles the switch.
So the SN is the clutch in the car.
Yes, that's a great way to put it. It disengages the DMN and engages the FPN so you can deal with the world. And Menon notes that if the SM fails to switch properly, which we see in pathologies like depression or schizophrenia, you might get stuck in your head with DMN dominance, or you might just be unable to engage with the world at all.
This helps clarify that flexible hubs concept from the review too, right?
It does. The FPN is described as a flexible coordinator. It shifts its connectivity patterns really rapidly to fit different tasks. It's like a social butterfly at a party talking to the vision department, then the motor department, then the language department.
And the CON SN?
They lend processing resources, but they're more stable. They are the backbone. They provide the stable architecture for the FPN to dance on top of.
Okay, so we have the whole architecture now. We've got the adjuster, the FPN, we have the maintainer and noise canceller, the Kulhan, the switch or the clutch, the SN, the spotter, DAN, and the circuit breaker, VAN.
It's quite the team.
It is. But what are they actually doing? We keep using these words like control and task sets. But if I could somehow crack open the brain and look at the files these networks are passing around, what would I see? What is a thought in this context?
That is the perfect question. And it brings us to section 4, cognitive control mechanisms. And for this, we have to turn to David Baudry's 2025 review. This paper gets right into the nitty-gritty of how this all works.
Baudry talks about representations, the actual files in the cabinet.
Right. And Baudry makes a really important distinction between two types of files or representations, compositional and conjunctive.
Okay, break those down for me. This feels really important for understanding learning.
It is. So compositional representations are like Lego bricks. You break a task down into its fundamental parts: color, shape, rule. If I tell you, press the left button if you see a red square, your brain loads the concept of red, the concept of square, and the rule that links them to an action.
That sounds really efficient.
It's flexible. It's incredibly flexible.
Yeah.
If I suddenly change the rule to red circle, you just swap out the square brick for a circle brick. You don't have to relearn the entire task from scratch, but it's slow. You have to consciously assemble the bricks every single time.
Okay, and the other type, conjunctive.
Conjunctive is integrated. You bundle everything into one single specific file. It becomes a red square press left file. You don't see the individual parts anymore. You just see the whole event and you automatically know what to do.
This sounds way faster.
It is much, much faster. This is automaticity, this is expertise, it's efficiency, but it's totally rigid. If the rule changes even slightly, you have to burn the whole file and start over from scratch, building with Legos again. And Baudry argues that the transition from that slow, flexible, compositional state, which is very FPN heavy, to the fast, rigid conjunctive state is essentially what we call practice.
So the FPN is sweating, building with Legos, trial after trial, and eventually it just hands a fully built 3D printed model to the rest of the brain and says, here, just use this from now on.
That's a perfect description, but you can't just let any Lego brick into the building room, right? Your working memory is incredibly limited. You need a bouncer at the door.
Gating.
Yes. Both Baudry and the Friedman and Robbins review discuss gating, and the bouncer, the gatekeeper, is the basal ganglia, specifically a part of it called the striatum.
I always thought of the basal ganglia as just being for movement. You know, Parkinson's disease, tremors, that sort of thing.
It is for movement, but it's also for cognitive movement. It acts as a gatekeeper for the prefrontal cortex. Baudry describes input gating, deciding what information from the outside world gets into your working memory. It's essentially locking the door to distractions.
Okay.
And then there's output gating, deciding when to use the information that's already in your working memory to drive an action.
And what tells the bouncer who to let in? What determines if the gate opens or closes?
Dopamine.
Of course it is. It's always dopamine.
It's always dopamine. Dopamine signals, specifically what we call reward prediction errors, train the basal ganglia on when to open or close that gate. It's basically your brain learning over time, hey, paying attention to this piece of information was useful before, so let it in.
So we have the files. We have a bouncer for the files. What happens when we screw up?
Performance monitoring. The oops signal. We touched on this with the FPN, but Baudry's review details the mechanism. It's a specific brain signal called the ERN, the error-related negativity.
That sounds like a very pessimistic outlook on life.
It's an electrical spike that comes from the medial frontal cortex, and it happens about 100 milliseconds after you make an error, which means it happens before you even know consciously that you messed up. Your brain has already fired this signal.
What triggers it? How does it know?
It's a mismatch. The brain is constantly comparing the action it planned to execute with the action it actually executed. If they don't match, it fires the ERN. And that signal is sent straight to the FPN, the quarterback, with a message that basically says, slow down, focus harder on the next play. This is why, after you make a typo, you usually type a little slower for the next few words. It's called post-error slowing.
It's just amazing that this whole feedback loop happens faster than conscious thought.
It is. It's the inner loop of control that keeps us on track.
So let's zoom out a little bit. We've been talking about these really specific networks and mechanisms. But in the real world, we use words like willpower or focus or multitasking. From a neuroscientist perspective, are these all just the same thing?
And that brings us to section 5, unity and diversity. Friedman and Robbins tackle this exact question head-on.
And I'm going to guess the answer is no, they're definitely not the same thing.
You are correct. They propose a unity and diversity framework. There does seem to be a common cognitive control factor, a general ability to maintain goals and inhibit responses.
So like a general self-control muscle.
Exactly. And if you're good at this, you're generally good at self-regulation across the board. This common factor links very strongly to the brake in our brain, a region in the right inferior frontal gyrus, or RIFG.
But
But then there are specific dissociable skills. They identify shifting, the specific ability to switch between mental sets, and updating, the specific ability to replace old information in your working memory with new relevant information. And here is the real kicker. They've shown that these three components are genetically distinct.
wait, really? So I could be genetically predisposed to be really good at focusing high common CC, but be terrible at multitasking or
Alignment.
shifting?
Absolutely. And you see this all the time in the real world. You know that person who can do deep work for 4 hours straight, but completely falls apart if the phone rings. That's high common CC, but low shifting ability.
And the opposite, the person who can juggle 12 chat windows but can't sit down and write a novel.
High shifting, but maybe lower common CC. It's not a single skill.
Wow,
That
that
one?
explains so much about pretty much all of my coworkers.
It also relates to another important distinction they make, which is hot versus cool control.
This sounds like a Katy Perry song.
It's a crucial distinction in the literature. Cool control is what we've mostly been talking about. It's run by the DLPFC. It's abstract, rule-based, logical, sorting cards by color or doing a Sudoku puzzle.
And a hot control.
Hot control involves the orbitofrontal cortex, or OFC, and the ventromedial PFC. This is value-based, emotional, and reward-driven control. Resisting a donut, deciding whether to take a risky bet in a gambling task, controlling your temper when someone cuts you off in traffic.
And they're actually chemically different systems?
They are. Friedman and Robbins do a great job highlighting the neurochemistry. Dopamine, as we said, is vital for that gating and updating in the cool PFC system. But norepinephrine is absolutely crucial for the stop signal for inhibition.
And serotonin.
Serotonin is heavily involved in what's called reversal learning. So changing your behavior when the reward rules of the world change.
So if your serotonin system is off, you might just keep pushing the button even though it stopped giving you a pellet.
Exactly. You get stuck in a rut. You can't adapt to the new reality.
Okay, we have covered a massive amount of ground. Let's try to synthesize all of this for the listener. Section 6, the outro.
Let's bring the whole boardroom back together.
Okay, so I'm sitting at my desk. I'm trying to write an important report. Walk me through it.
Okay. First, your salience network, SN, the switch, detects that the deadline is approaching, which is a highly salient event. The clutch engages. It actively suppresses your default mode network, DMN, so you stop daydreaming about your vacation, and it engages the control networks.
Okay, I'm engaged. The machine is on.
Now your frontoparietal network, FPN, the quarterback, looks at the blank page and sets the immediate plan. Open the document, type the title. It is managing all the rapid moment-to-moment actions. It is building those compositional representations, linking the idea of a letter to a key press to forming a word.
And in the background, the hum.
Your cingulo-opercular network, CON, the stage manager, comes online. It sets the stable work mode. It turns on those alpha wave windshield wipers to suppress the sound of the air conditioning unit and the urge you have to check your phone. It's maintaining your tonic alertness.
Okay, I start typing, and then I make a typo.
Your error monitoring system in the medial frontal cortex fires an ERN. The FPN catches that signal, slows you down for a split second, and you hit the backspace key to correct it. That's post-error slowing in action.
My phone buzzes on the desk.
The ventral attention network, the circuit breaker, screams, tiger, or, text T. Your basal ganglia, the bouncer, now has a decision to make. Do I open the gate for this distraction? If your common CC is strong, you inhibit that impulse. You keep the gate closed and stay on task.
And I finish the report.
And you feel tired.
Wow.
Which brings us, to our final thought.
Yes, back to the von Economo neurons.
We mentioned earlier that these special neurons in the con are rare, they're evolutionarily new, and they seem to support that long-term maintenance of state.
The ability to pursue a goal not just for minutes, but for months or years.
Exactly. So here is the provocative thought for everyone to take away. We often think of burnout as an FPN problem, an overload problem. Too many tasks, too many emails, too much to process. But maybe burnout is actually a failure of the con.
A failure of the stage manager.
What if the con is responsible for maintaining the state of being a worker or being a parent or being a student over these very long periods? Maybe what breaks isn't the ability to do the task anymore, but the ability to maintain the mode required to do it. The von Economo neurons just quit. They can't keep the stage set anymore.
So when you say, I just can't do this anymore, you don't actually mean I can't type. You mean I can't hold this set. I can't be in this mode for one more minute.
It's a hypothesis, but it suggests that protecting your tonic alertness, your ability to truly disconnect and let the stage manager reset, might be just as important, if not more important, than just training your FPN to work faster and more efficiently.
That is definitely something to mull over on your next commute. So listeners, ask yourself today, are you in rapid adaptive mode or are you in stable maintenance mode?
Yeah.
And maybe more importantly, is your stage manager getting a coffee break?
Special thanks to the work of Dosenbach, Satagiani, Menon, Friedman, and Badre for providing the map to this very busy boardroom.
We will see you next time on The Deep Dive. Stay alert.
And keep your gates managed.